continue to undergo a rigorous quality control process. The design has been reviewed by an experienced independent third-party review board and will be reviewed by the Alberta Dam Safety Regulator. Failure modes of the individual components and the complete system have been considered in the design, and features and mechanisms have been implemented to mitigate potential risks. During design of a dam, we consider potential failures such as dam overtopping or erosion of the embankment, and then design to prevent these failures. For example, the emergency spillway is sized to pass the full probable maximum flood event safely. That's without consideration of the ability to close the diversion inlet gates. This provides a secondary level of protection against the dam from overtopping in the event that the diversion inlet gates do not close. Further examples include the addition of resilient and redundant systems for the mechanical and operating components of the project, such as backup power to ensure that gates can be operated even during situations where a storm has affected the electrical grid, remote, local, and manual control options for the gate systems to be operated from the control building or the structure, and manually should computer systems fail. In addition, multiple layers of debris management begin with the debris deflection barrier that excludes large debris from being diverted into the reservoir. Further, the diversion structure has been designed to pass debris without hindering operations. And finally, the trash racks located on the low-level outlet provide an additional layer of protection at the dam. During construction, quality assurance and quality control programs will be in place to monitor compliance with the design. Instrumentation will monitor the performance of the dam earthworks and foundation. Monitoring of instrumentation will continue after construction and through the life of the facility. In operations, maintenance, and surveillance program will direct routine operations for the structure and direct regular maintenance requirements. Under the regulatory requirements in force in Alberta, the owners of dams need to undertake dam safety reviews at regular intervals to maintain their license to operate. As an extreme consequence structure, the dam safety review for SR1 will occur at minimum once every 5 years. The dam safety reviews include a review of the hydrologic estimates made for the inflow design flood. The province of Alberta has a robust emergency management program for all dams within the province. As the operator of SR1, Alberta Environment and Parks will prepare an emergency preparedness plan, an emergency response plan, and a flood action plan that meet the regulatory requirements for extreme consequence facilities as stipulated in the Alberta Dam and Canal Safety Directive and the Government of Alberta's Operational Plan for Dam Safety. The preparation of these plans will involve consultation and coordination with downstream stakeholders in the same manner that is required at all their facilities. The emergency management plan, emergency response plan, and flood management plan will be prepared by AEP following regulatory approval of SR1 when construction procurement is complete and the project is closer to commissioning. This is because the plans require information on equipment models, construction records, and other details of the facility that are not finalized at this time. As you know, Mr. Chairman, the SR1 Concerned Landowners Group retained Austrian Engineering to review the design and planned operation of SR1 to identify risks and recommend improvements in the dam safety aspects of the project. Stantec carefully reviewed the Austin Engineering report and provided a detailed response in a technical memorandum, which was included as part of Alberta Transportation's reply submission. Our technical memorandum is in Exhibit 327 at Appendix E. To summarize our response briefly, we disagree with the suggestion that the design of SR1 fails to meet any Canadian Dam Association safety guidelines. With respect to the recommendations made by Austin Engineering, we've concluded that no changes to the design of the project are necessary. However, we acknowledge the effort that Austin Engineering obviously put into their review, and for that reason, on March 19th, 2021, Alberta Transportation provided the report, together with Stantec's response, to the AEP dam safety review team that is reviewing the SR1 design for their information and consideration. Thank you.
Thank you, Mr. Manager. Mr. Chairman, that completes the opening statement of Alberta Transportation and topic session 3. The witnesses are now available for cross-examination.
Thank you. Now, I'm assuming that Calgary River Community Action Group, City of Calgary, don't have any cross at this point. Is that correct?
It's Lou Cassano, sir. Yes, that's correct.
Ms. Senden?
Mr. Chair, this is Sarah McKittrick speaking. I believe Ms. Sinek has just stepped away. I do not believe we have any questions either.
Okay, thank you. Ms. Loudon with Stony Nakota.
No, Mr. Chair, we do not have any questions.
Thank you. Mr. Secord?
Thank you, sir. This is Rich. For those of you who are new on the panel, my name is Richard Secord, and I am counsel for the SCLG group. Most of my questions I expect to start off with will be perhaps for Mr. Manager, but Mr. Hebert, I think you're the quarterback, so feel free to direct the questions as you see fit.
Mr. Secord, so just before we continue, Ms. Vespa, are you okay with Mr. Secord's voice? The volume, you're good? You can hear him? Okay.
Great.
And Mr. Secord, I recall, or from my table, it shows that there was a significant amount of time that you had designated to topic number 3, so which was all approved. So I mean, that'll take us for sure through today and then into tomorrow. But I'll proceed, and then we'll just break it for the afternoon at some point, just to give people time to stretch, have a washroom break. But I'll try to pick a time that seems to work with testimony and questions.
Thank you, sir.
Thank you.
What is a diversion inlet rating curve?
Sure, I can take that. So this is John Manager. So a rating curve is a relationship between elevation of water and the flow and a discharge through a structure. So when you referenced the diversion inlet rating curve, simply speaking, that means the water upstream of the diversion inlet correlates to a specific flow rate that's going through the diversion inlet structure. So at elevation 1215.8, 600 cubic meters per second would go into the diversion channel.
Document manager, perhaps we could pull up exhibit 159, PDF page 100, figure 19. And perhaps you could get figure 19 in the center there and sort of enlarge so we can read the fine print. Thank you. Now, Mr. Manager, I believe you were involved, you've been involved since 2017, correct?
Since 2014.
Right. And you would, I'm sure, be familiar with the diversion inlet rating curve that was filed in March of 2017 in the preliminary or the draft EIA, correct?
Yes.
Between the 2017 draft and final preliminary designs, an access bridge has been added over the diversion inlet with a bottom elevation of 1,215.5 meters, correct?
It was in the 2017 design as well, Mr. Seaford.
Okay. And the addition of the access bridge to the design, did that not result in a decrease in the discharge shown in the rating curve at the water surface elevation of 1,216 meters?
It did not. I do not believe the rating curve actually has changed between the two timelines.
Has the impact of the bridge been accounted for in the analysis?
Yes.
And what was the anticipated reduction in intake flows as a result of adding the access bridge to the design?
So as I stated previously, the bridge has been an integral part of the design from the beginning. It purposely is set at the given elevation. The curvature of the upstream support structure for the bridge is intended. It has a rounded edge to the front side of it, but in general, the purpose of the bridge is twofold. Number one, it does provide access across the structure for vehicles, trucks, cranes, other elements of maintenance vehicles, and provides access across. But the second piece that it does is that the upstream support for that bridge member is what's known as a breast wall. What that does is that breast wall helps to limit flows at higher elevations from entering into a structure. It can change something going from a weir flow to orifice flow, which actually would restrict some flow. So it's intentionally set at an elevation where it doesn't affect our ability to divert for the design flood, but at higher elevations would reduce the risk of additional flows entering the structure when elevations increase.
What do you mean by a weir flow?
Sure. So a weir is so if you think of it as a water flows over top of it, as a lot of times they call them sharp crested or broad crested weirs. It's a flat or sharp angle that water flows over. That the shape of that weir and its length dictates how much flow would go over it for a given elevation. An orifice, on the other hand, is a hole that water has to flow through. So it has to go through. So instead of just having that surface friction on the bottom, has it all around all the sides, and it restricts the flow and it causes flow to slow down further. In simplest terms.
And in this case, what type of flow do we have?
Primarily, it functions as weir flow for the majority of it. But as I said, if you were ever to get water surface elevations that would exceed the design, so for our intents and purposes, that 1215.8 is intended to be the 600. I will note, as you mentioned, the bottom of the wall is 1215.5. What you will see, though, is that this curve is not set immediately at the wall. It is upstream before you have the influence of drawdown into the structure and through it. And so when we tested this in numerical models and in physical models, what we observed was that at the breast wall and at 600 cubic meters per second, the water surface elevation doesn't touch the wall. So
sorry, again, and in relation to figure 19, which we have up on
Yes.
the screen, can you explain to the panel how the curve works and exactly what you're referring to when you gave that answer a moment ago in relation to the curve?
Sure. So this curve, as I mentioned, on the left-hand side is water surface elevation. That's the water surface elevation upstream of the diversion inlet. So that's what controls flow into the channel. that is measured at a distance far enough away from the structure that it doesn't have that drawdown effect. So in this case, it's about 20 meters or so upstream of the structure is what that elevation is in reference to. And then on the x-axis on the bottom is the discharge through that structure. And so in this case, if you come across and you would follow, if you picked an elevation, we can pick 1213. I would select the 1213 number, and then I would go across that grid until I intersected the blue line. At that point, that would tell me what number I would have to read off of the bottom axis. So in this case, at 1213, you would have 120 cubic meters per second going into the diversion channel.
And the bridge, the access bridge, has an elevation. It has a water surface elevation of 1216 meters.
I believe the bottom of the bridge is at 1215.5, Mr. Secord.
Okay, so if we go to the bottom of the bridge at 1215.5, that would mean that the discharge rate would be something in the order of
Yeah, 550 or so.
550 cubic meters per second.
Yep, but as I said, that this is not measured at the bridge. It's measured, the reference point is slightly upstream of the bridge, and there is a drawdown effect that occurs between the two structures. If that helps.
And the bridge is actually going over the inlet gates to the reservoir, correct?
That's correct.
And
well, I'm sorry. Let me rephrase that. The bridge goes in front of the gates, not over top of the gates. In front of.
And does the bridge then operate as a barrier to flow above 1215.5, a water surface elevation of 1215.5? Does it operate as a barrier to water flow?
Yes, yes, intentionally so. But as I said, that's for when the water is at 1215.5 at the bridge. That's not what this curve is referencing. This curve is referencing a point upstream of the bridge that's away from the influence of the drawdown down and through the structure. So the hydraulics here is important to note that. And so it is not restricting flow at our design flood elevation of 1215.8. As I said, we observed that drawdown effect in both our hydraulic models, both the numerical computer models and the physical model that was produced for this project, and demonstrated that we can pass the correct amount of flow through the structure at the designed elevations.
And you said that the water surface elevation, or the WSE, that is measured at a 0.20 meters upstream of the bridge.
It's, I think, roughly subject to check, but yes, it's upstream of the bridge, not right at the face of the wall. That's correct.
And how is it measured? What is in other words, how is the measurement taken and communicated to the eventual operator of the facility?
Sure. So we're going to have multiple locations for water surface measurement for the project. I am telling you that this hydraulic rating curve is based off of that point 10 to 20 upstream of the structure. When we produce the required instrumentation and controls for the gate systems, we have locations proposed for our instrumentation. We'll have several that are located and mounted to the debris barrier in and around that location that can be above the water level using ultrasonic measurements to shoot down towards the water surface elevations to capture those locations. And we'll utilize our tools, hydraulic modeling tools, to relate that elevation to the rating curve, and then allow for the operators to make decisions with regards to operations.
And you mentioned 10 to 20. Is it 10 meters before the access bridge or 20 meters? And maybe I should just ask you, is there somewhere in the application materials which would give us, which would pinpoint the exact distance? And rather than taking time, would you be able to undertake to advise me what the exact distance is? Maybe
I don't,
after
it
the
does,
break?
I can advise you, Mr. Seedcord, that it doesn't matter. The elevation difference 10 and 20 meters upstream of the structure it will be the same. It's the water surface profile in that location has a slope that would be imperceptible. And so we could call it 20 meters. And I think that would be fine.
And does that slope change in the 20 meters from the point where it's measured to the point where it hits the access bridge? Does that slope change?
Yes, like I
And
said,
how-
it's a drawdown effect that
what-
was observed.
And what would be that drawdown effect? Is there a graph that would show the drawdown effect in that 10 to 20 meters?
Yes, I could point you to exhibit. Let's see, make sure that I get it correct for you. Exhibit 174, which is Appendix C of the preliminary design report, the hydraulics section. And it is page 70 of the PDF, is a good illustration of the effect.
All right. And in relation to the diversion inlet rating curve that we see here, were the water surface elevation at the measuring point 10 to 20 meters upstream, say it was at 1,217 meters, that would provide a discharge rate at that point of something in the order of 800 and let's say 80 cubic meters per second. Would that amount of water be accommodated in that drawdown to be able to go entirely into the reservoir, or would you see some of that water going into the spillway at an elevation of 1,217 meters?
Sure. So I will say, so number one, the structure is not intended. The design operations parameters for this project are not to allow the flows to exceed 600 cubic meters per second. As such, we would close the gates to prevent flow from exceeding that number of 600. So number one, we would not intend to do that. In the reason this diversion inlet rating curve extends to that level was so that we could analyze the potential effects of a malfunction of the gates and a failure for them to close. In this scenario, that would represent that 1217 is slightly greater than what the probable maximum flood would produce at this structure. So in that case, that amount of flow could flow into the channel. What we did analyze within the preliminary design report was in that scenario, we confirmed that the discharge channel could contain those flows, that none of the embankments or sidewalls of the channel would be overtopped during that extreme scenario. And again, as I said, not a planned scenario, that would be a malfunction. of the system, and we do not intend to push more than 600 down through it. But if it were to enter the channel, it would flow to the reservoir up until the point that the reservoir was completely full up to the emergency spillway, and then flows would discharge through the emergency spillway. And we've demonstrated that within our application.
So do I understand then that the water surface elevation of 1,217 meters that is shown in figure 19, that essentially represents the flood of record, the June 2013 flood?
No, I think this is what I'm telling you. This is the flow only through the diversion inlet structure. This is not all the flows that are in the river. Under the scenario of the flood of record, the June 2013, where we estimate that the discharge in the Elbow River was 1,240 cubic meters per second. Our design approach would be to pass 640 cubic meters through the service spillway, which is in the river, and then 600 into the channel. So that would occur. So our goal then would be to use the gates of the service spillway to produce a water surface elevation of 1215.8, which represents 600 cubic meters per second going through the diversion inlet.
And what happens to the water then that is above the 1215.8?
There is no water. That's we're not raising the water above 1215.8. We're setting it. The elegant solution about SR1 in the proposed operations scheme is as water flows down through the Elbow River, we're measuring it. When it gets to an elevation that we know represents 160 cubic meters per second at the service spillway, we open up, or slightly prior, we open up those gates on the diversion inlet. They are fully open. We then use the gates in the river to raise the water surface elevation slowly to control the flows into the channel. This curve basically tells us at any given elevation in the river, that's how much flow is going into the channel. And so when we want to hit a constant diversion rate of 600 cubic meters per second, what we have to do is just operate those gates in the river to keep the water level at 1215.8. So if it starts to get above 1215.8, we lower the gates. If it gets below 1215.8, we raise the gates. That's in simple terms, we use the gates in the river to control the water level.
But the bridge bottom is at an elevation of 1215.5. So how much freeboard is achieved at the design flow?
Well, as I said, the bridge has no effect on the flow during the design flow. The water's underneath it. And as the figure I referenced and gave you reference to shows, and the physical modeling demonstrates, that was produced. So the water doesn't hit the structure and it doesn't affect it. In terms of freeboard, when we reference freeboard, what we're worried about is where that water will go and impact. It doesn't impact the bridge. The bridge has been designed for impact loadings from large trees and vehicles. The bridge is not affected by these structures. It's designed to withstand impacts from flows much higher. What we're worried about would be water going over top of the height of our walls. And so those walls have freeboard of 1.5 meters to 2 meters. They're up to 1219 something. They're up to 1219. And so those are the pieces that we are focused on in terms of freeboard.
And where is the individual or individuals who would be operating the gates? Where will they be located?
Sure. So they have a couple options. Number one, we have a control building that's located in the parking lot adjacent to the service spillway and the diversion structure. Document manager, it might be helpful. I mean, I guess it's up to the questioner here, but and I can describe it. There's a parking lot adjacent to the two gates.
Do you have a reference?
Sure. One of the drawings from the preliminary design report would work well.
Sure.
Let me find the number for you. So that would be exhibit 159. PDF 283. 283. All right. So what you see on this drawing is on the bottom of the drawing is the service spillway and the Elbow River. The water is flowing left to right. At the top of the page is the diversion channel. And
just before you go, it's a little overwhelming here, all of this information. I do see the parking lot.
Yes.
There's a parking lot that appears to be north of the what they call the service spillway.
That's correct.
And can you maybe so we've got the debris deflection barrier there on the bottom left.
That's correct.
And and just help me out. The gates would be shown just, I guess, above the debris deflection barrier.
Yes. So you have the debris,
and let's just tie in the access bridge.
Okay, so that hatched area, that kind of grayish area that goes over top of the white, there is the access bridge, and the gates are just downstream. So
right where we see the words 10 plus 100, just below diversion inlet.
Yeah, it's more of where that plus sign is, if you will. That's basically where the gates are. You can sort of make them out there.
But the bridge, is that the bridge that you're referring to?
The bridge is down. The bridge is below that. It's that hatched area where you can see the two kind of gate symbols on either side of it. That's
right.
Yeah.
I got you. So basically, just to the would be to the west of the parking lot.
Yes. Yep. It connects the two. It connects the two sides. That's right. It connects the parking lot to their side, and so you can see the control building is shown there in the parking lot.
Great.
Yeah.
And so then if we could go back to figure 19, document host. We were just at that page. There we go. So you've got your people in the parking lot operating the height of the gates. Can you tell me if they mismanaged the operation of those gates, could the water surface profile actually hit the access bridge?
Yes, intentionally so. The access bridge is supposed to restrict flows if they get higher.
And then what happens with that water once it hits maybe we'll go back to
sure. So
let's go back to the other diagram.
Yeah, sure, absolutely.
Host.
So when you restrict flow into the channel.
Just 1 second, PDF page 283.
So it's a balance game here, right? So when you restrict flow into the channel, the flow that doesn't get into the channel stays in the river, and so it goes downstream. So in this case, if every bit of flow that we restrict just continues through the service spillway gates and downstream, would be the simplest explanation.
And in relation to the service spillway area, I take it all of that water then runs eventually, does it overland to the Elbow?
The service spillway is within the Elbow River.
Right. And when
the Elbow River flows through it.
And when would the design spillway, when would that ever be engaged?
I'm not sure what you're referring to as the design spillway.
So is the service spillway the entire spillway?
Sure. So the portion of the structure that's within the Elbow River floodplain is a combination. We refer to it as the service spillway, which is the set of gates that are in the river that I just mentioned that go up and down and control the water level within the river itself. Adjacent to the service spillway is a structure that's called the auxiliary spillway. That structure is at a much higher elevation. So the service spillway is at 1210. The auxiliary spillway does not activate until 1216.5. I know I'm throwing a lot of numbers here, but 6.5 meters above the service spillway, and above what our design operating levels are. So if water continues to get higher than we intend to operate the structure, it would flow over the auxiliary spillway to provide a secondary a secondary flow path for water within the river, and to keep the water surface elevations upstream controlled. Adjacent to past that is the floodplain berm, which is positioned at a high enough point so it will not overtop. And so the service spillway and the auxiliary spillway control the flows within the river. Everything that goes over those two goes downstream and stays within the Elbow River channel and floodplain area.
So in this case, if water hit the access bridge, it would simply be falling back into the service spillway, correct?
It's not quite falling back. Like I said, it's restricting the flow, similar to if you had a hose that had a certain size and you squeezed it down a little bit, you would restrict some of the flow that goes through it. It's yeah. So it's whatever, if you have 100 and you have 30 that goes in the channel, 70 continues in the river. Now, if you had 120 and you still wanted to restrict it to 30 in the channel, then you would have 90 in the river. It's just a simple split of the flows.
If the water hits the access bridge, how have the impacts of friction been included in the diversion inlet rating curve?
Sure. As I said, we perform the appropriate calculations to look at the effects of whether it's weir flow or orifice flow, and we performed hydraulic modeling that incorporates those physical processes to confirm those effects.
And what is the elevation of the debris deflection barrier?
Don't have it immediately off the top of my, give me 1 second.
Actually, Mr. Chairman, it's Wayne Speller. I was going to suggest maybe we caucus for a minute. Because we have so many virtual witnesses, we're going to jump into a breakout room very quickly. We won't dawdle.
And I have one, while you're in your breakout room, I have one matter you might just take up at the same time. If we could go back to the rating curve, figure 19. Now you mentioned that the auxiliary spillway elevation was 1216.5, Mr. Manager. Correct? It looks like, Mr. Chair, it looks like they've already taken their break.
No,
So,
some have. We'll return in a minute, Mr. Chairman.
okay. I lost them, sir.
So what do you need for time?
Well, I don't need any time, but
No, not you, Mr. Secord. They're already.
Well, Mr. Chairman, I suspect we'll be quite quick.
Okay.
It's Matt Hebert. Sorry.
Yeah. All right. Thank you.
Mr. Chairman, it's Matt Hebert from the Transportation Panel. I suspect our witnesses are now going to be re-emerging from the breakout room.
Great, thank you.
Yep. So Mr. Secord, I'm back. Your question again was with regards to an elevation. What was the structure?
So I believe you indicated that the service spillway, or sorry, yes, the auxiliary spillway elevation was 1216.5, correct?
That's the top of the pilot channel for the fuse plug. That's correct.
And so looking at the diversion inlet rating curve at 1217 with a water surface elevation of 1217 meters, I take it then that would push water into the service spillway. Sorry, the auxiliary spillway.
Sure. At 1217, there would be water flowing through the auxiliary spillway. That's correct.
Right. And when I looked at the original, auxiliary spillway, it seemed to me the original design took the spillway right up to the edge of the Elbow River, but the current design has the auxiliary spillway not going to the edge of the Elbow River. So it looks to me like if you're pushing water into the auxiliary spillway, that water will have to flow towards the Elbow River and flood my client's lands. And I'm just wondering why doesn't the auxiliary spillway go in the PDA go right down to the edge of the elbow?
Oh, Mr. Secord, I believe we have a confusion on spillways. So we have there's a lot of structures on this project.
Okay, well, let's go back to PDF page 283.
Yes. So you can't view the auxiliary spillway on this. So let me give you a different number so we can talk to it together. So bear with me one moment. Okay, so document manager, if you could go to page 262. All right. So this is a larger view. You can see the Elbow River running from left to right. The floodplain berm runs from the bottom of the page at the 0 plus 600 and runs from left to right to about a little bit more than 1 plus 600. Then the auxiliary spillway runs until it intersects with the service spillway. So the auxiliary spillway still is within the Elbow River floodplain and still is adjacent to the service spillway. So the way that the project functions is the floodplain berm constrains the flow within the Elbow River and directs it towards the service spillway. The service spillway is used to control the flows, the elevation of the water within the river, which then pushes some flow into the channel. At a very large flood, the gates from the service spillway would lower completely to the bottom of the river channel. At that point, the majority of the flow would continue through the service spillway structure But if waters continue to rise, then they would overtop that auxiliary spillway and provide a secondary outlet. And that what that does is that allows us to reduce the amount of flow that goes into the channel, and in combination with that the breast wall / bridge that we've been talking about a lot, to all function to keep the water levels in the river to a certain level to prevent overflow, to prevent too much water from going into the channel. If you go further down the channel, the emergency spillway is located along the channel and really an extension of the reservoir and dam. That structure is the belt added to the suspenders. The intended operations of this project is to stop flows from entering the channel once the reservoir is full, so the gates close. We have a lot of provisions in place to make sure that that happens. The debris deflection barrier will keep debris from clogging or blocking the gates from closing. We have primary and backup power. We have the ability to lower those gates under their own weight without any power and using manual brakes on the gates. But in all of those scenarios, if water still enters the channel and the dam is up to the emergency spillway elevation, at that point, water would go over that emergency spillway and then it would be redirected back to the Elbow River again. But as I said, that would be in an extraordinary large flood event and would constitute a malfunction or failure of the project to operate as proposed and intended.
All right, so which figure, what's the number of this figure? I'll scroll down just a little bit or up, I guess. I would always get it wrong for the document manager in the direction. It doesn't have I guess it's just called diversion structure overview.
Yeah, so the drawing number would be C201.
Okay, so and it says preliminary design, not for construction. And when was this? This was drawn on the 25th of September last year.
Yep.
Okay, so we could go down document host. Do I have it right? Scroll. No, I guess up then. Sorry. Great, thank you. So we have the Elbow River basically running through the top portion of this figure, correct?
Yep, that's correct.
And we have the river hitting the debris deflection barrier. And then we have the bridge, the access bridge, just to the, I guess, west. I guess in this case, it would be sort of north.
Yep.
I guess the direction of the map actually shows north going from left to right. So it would,
yes.
It would be, I suppose, more or less west. The parking lot would be then to the east of the gates, letting the water into the reservoir.
Yep.
And under normal operations, the service spillway then would take what isn't being diverted into the reservoir. It would take the river flow off to the east down the Elbow River, correct?
That's correct.
And then you have what you call the auxiliary spillway, and you gave me the elevation of 1216.5. Is that still right?
Yes.
And is this what you call the emergency spillway?
No, it's the auxiliary spillway. The emergency spillway is on the channel. It's a completely different structure.
And is that shown on this?
Not on this drawing, no. I could give you a reference to a different drawing to show you where that's at, but.
So before you mentioned there were a lot of spillways. So what is the auxiliary, the function of the auxiliary spillway doing?
As I said, it adds capacity in the river to pass additional flow downstream. So when water gets above 1216.5, more flow will go down that way. And that in turn makes sure that our water surface elevations upstream of that structure are low. And so it reduces the amount of flow that goes then into the channel.
So if we look at, I think we know the figure 19 off by heart now, but at an elevation at 1217, at the gates, that would mean that water would be being pushed into the auxiliary spillway. Would that be correct? Or would be overtopping the auxiliary spillway?
That's right. Yep.
And where does that water go?
It goes
once it overtops the spillway.
It flows through the historic Elbow River channel floodplain and back to the primary channel.
Okay. And is that area entirely within the PDA?
No, it's not.
And would any of my clients be subjected to flooding as a result of the auxiliary spillway being engaged?
Mr. Chairman, I can confirm that none of the SCLG clients would be affected by it.
What about the landowners who are there?
I don't know who was speaking.
Oh, my apologies. It was Matt Wood.
What about the landowners who are there, Mr. Wood? Would they be subjected to flooding?
In the case of the auxiliary spillway, you can see it in the contours and how it's graded there. When the water spills over it, it takes the floodplain area and is directed back into the river.
So what's the answer to my question?
I will say, and I guess Matt, this is John Menninger, that in that scenario, so again, if the auxiliary spillway is activated, we're looking at an event that's in excess of a 500-year flood. Areas that are within the floodplain downstream, regardless of property line, would be inundated with water that within the river system. So we have looked at the areas generally of impact, but it would flow through the river as mapped, as typically shown.
Document host, if we could go back to figure 19, please. Well, you said that engaging the auxiliary spillway would be something in the order of a 1 in 500 year flood, Mr. Menninger. But when I look at the diversion inlet rating curve, at an elevation of 1217, the flow is only 900 cubic meters per second. And I thought the flood of record was coming down at 1260 cubic meters per second. So how do you get to a 1 in 500 year flood when the water elevation is only at 1216.5 meters?
Sure. So again, this is the flow that's going into the channel. So during a 500-year event, you would have 1800 coming down the river, and that flow would be split between a series of 3 structures. And so a portion of that flow would be going down through the diversion inlet, when would fall within this rating curve. And then a portion of that would flow downstream and through the service spillway and auxiliary spillway. As I mentioned, we would not intentionally operate the structure to exceed 1215.8, which is shown here. And so you would have 600 going through the diversion inlet and 1200 going through the service spillway. So on this curve, during an operating condition, when we intend to divert flow into the channel, you would be at 1215.8 and putting 600 into the channel. The 1200 would go into the service spillway.
Right, Mr. Manager, what happens if the diversion inlet gates are opened due to operator error, instrumentation failure, etc., when the off-stream storage reservoir is at F and at an FSL of 1210.75 meters?
I'm not sure of a scenario of I don't know why you would have an unintentional operation. These are enormous structures. Our gate systems would have programming in effect that would in effect lock it out from raising them in a scenario where you would already have the reservoir full. Alarms would be going off. And then on top of that, you would have to have a flood operating. You would be trying to push flow into it. So that said, we have the emergency spillway located on the channel that will discharge flows that are in excess of 1210.75, which is that full service level, as you mentioned, of the reservoir.
Now, you can turn this up if you want, but reservoir routing scenarios are presented on page 27 and 28 of Exhibit 327 and in section 10.1.3 of Exhibit 159. And they indicate a constant diversion maintained at 480 cubic meters per second based on incremental closing of the gates. Do I have that right?
Could you repeat the page number, please, Mr. Secord?
Pages 27 and 28 of Exhibit 327 and in section 10.1.3 of Exhibit 159.
Well, I think we need to do one document at a time. So which one do you want?
I didn't want either of them.
Well, you refer the witness to them and you say, if you want, you can look at them. I think to be fair to everyone who's watching, we should look at a document. And why don't we start with the first one?
Sure.
Okay.
You might want to scroll down. Document host. There we go.
Perhaps Mr. Secord can ask the question again now that we're looking at the document.
So reservoir routing scenarios are presented on pages 27 and 28 of Exhibit 327.
Yep.
And they indicate a constant diversion maintained at 480 cubic meters per second based on incremental closing of the gates. Correct?
Yes.
Why has Stantec not applied the design diversion rate of 600 cubic meters per second for reservoir routing scenarios in favor of 480 cubic meters per second?
Either scenario would function well, Mr. Secord. So we have in this scenario, so I'll explain the purpose of this, these two figures. So this first figure, shown figure 1, is the probable maximum flood. So again,
document host, could we scroll down or up?
Yeah. So as I think we've discussed previously, but to repeat, the probable maximum flood is generated is what's used to design structures and spillways for an extreme consequence dam. So in this scenario, we're modeling what would occur during a probable maximum flood if the structure were to operate for a period of time until the diversion closed. As I said, that is the proposed and intended operation for the structure. I will stop to say it, I guess, to explain that the design diversion rate is between 400. So the necessary diversion to mitigate for the 2013 flood is 480 cubic meters per second. We have the ability to pass 600 through the channel as needed and as appropriate for operations. That buffer, that 25% buffer, I think, as we have explained previously, was to allow for some flexibility in operations, to allow for potential impacts from sediment or debris at the time of consideration. And so the operators will have some flexible range to operate the structure. So in this scenario, if you were operating underneath a probable maximum flood, it would not be ideal to fill up your reservoir before the peak of the flood hits. So in this scenario, we're showing that they're diverting at 480 to fill up the reservoir and take off some of the volume. This scenario represents, on the blue line, represents the flow that's into the diversion structure from during that operations. And so basically what you're seeing is that the blue line represents the flow into the through the channel and into the reservoir. And then at about simulation hour 50, 55 or so, the reservoir is full and the gates are closed. So the reservoir is filled, gates are closed. The rest of the flow that's in the river continues downstream.
So basically 55 hours in the event of a PMF, reservoir is full.
That's correct.
Okay. Do you agree that a simplified liquefaction triggering analysis can be used to estimate post-seismic deformated induced loss of freeboard of the dam based on the method of Rauch et al. 2007?
I'll defer to Mr. Back, who is on the line here, who is our geotechnical expert on the panel.
Hello, Mr.
Could you
Back.
please restate?
Hello, Mr. Back.
Good afternoon, Mr. Secord. Could you please restate the question for me?
I sure will. So do you agree that a simplified liquefaction triggering analysis can be used to estimate the post-seismic deformated induced loss of freeboard of the dam based on the method of Rauch et al. 2007? And maybe before you go there, could you indicate what is a simplified liquefaction triggering analysis? Maybe we could start there. And if you can, great. If you can't, that's okay too.
Well, let me begin by saying that liquefaction analysis is a little bit of a sophisticated partition of geotechnical engineering. While I have some general familiarity with it, that would have, if that had been appropriate, would have been performed by other engineers that work with me that had more familiarity with seismic engineering. I will say very adamantly that liquefaction is not a consideration with foundation soils, which we have here at the Springbank offstream storage reservoir. We have relatively stiff glacially deposited clays in large measure, and those will not be subject to liquefaction certainly not with the seismic events that we would expect here, or really with any seismic event.
And can you tell me what is a post-seismic deformated induced loss of freeboard of the dam?
I'm not sure that I would use that terminology as part of the analysis for the SR1 dam. We did seismic analysis in the way that's recommended by the CDA and other dam references. We looked first at what's called a pseudostatic analysis, where we simply apply a horizontal load when we're doing the stability analysis. That tells us that horizontal load is derived from the likely motions that would occur in the design earthquake. That will give us some indication of the likely stability of the structure in an earthquake. According to the CDA guidelines, if that does not meet criteria, which is a factor of safety of 1.0, then additional analysis is required. And the analysis that's performed at that point is a deformation analysis. Okay, that deformation analysis is what's, or the method we use, the common method, is called a Newmark analysis, which was developed by Dr. Newmark. That involves integrating the motions that occur during the design earthquake and establishing how much of that motion exceeds the pseudostatic factor of safety, and summing up the motion that would come out of each of those pieces from the time history of the earthquake. And that gives you a amount of settlement, loss of freeboard, if that's the term you want to use, that would occur during the design earthquake event. That was performed at SR1, and I believe the maximum deformation that we had was 0.3 of a meter. So that would, depending on the nature of the critical circles for your failure surface, would result in a loss of freeboard of up to 0.3 of a meter. There's a third analysis that's done, and that is a post-earthquake analysis, and that is after the motion stops, when everything is static again. We make the assumption that the motion has caused some reduction in the shear strength of the soils in the embankment and in the foundation, and a post-earthquake analysis is done there. That was also done at SR1, and those meet the criteria as well.
And what was the design earthquake of record in this case?
Again, I'm not the seismic expert. We retained some seismologists with Stantec. I think they were in British Columbia, that prepared a risk analysis, a seismic risk analysis for the project, and they identified the motions that were appropriate. I believe a 10,000 year recurrence interval event was used as the design event. I can't speak directly to where that motion occurred. There is source zones that those are developed from, and it would be a number of kilometers away from the site where that particular large motion would have been assumed to occur.
And you know what the magnitude of the earthquake was? That was the design earthquake in this case?
I believe it's a magnitude 6, but it would be probably more appropriately described by the particle velocities that occur during it. I'm not immediately conversant with those numbers. I could look it up and get back to you with how that event would be characterized. It's in the submitted report. There's the entire seismic risk analysis report is included in the submission.
When and at what stage of the design does AT expect to submit to the, and I don't know if they'll be submitting it to the NRCB for review, but when does AT expect to submit the draft OMS manual?
Don Manager may be better.
Yes, Stan, I was going to say I'll field that. Based off of the terms of reference and our understanding of the regulatory review process, the operations, maintenance, and surveillance manual was not a part of the application for the Natural Resources Conservation Board. We did not submit it, and as I understand, the board has recognized that there is another regulatory entity that has purview over the dam safety arena. Alberta Environment and Parks Dam Safety Division will review the operation, maintenance, and surveillance manual prior to authorization to operate.
And would that be the same for the draft safety management plan, the storage dam commissioning plan, the off-stream reservoir dewatering plan, draft DEP, would those all be submitted to AEP at some point?
That's correct.
Mr. Chairman, just one brief moment. Mr. Chairman, Matt Wood will supplement the answer.
Thank you, Mr. Chairman. If I may, just going to request that Mr. Secord repeat the question. I was playing with my mask.
Sure. I was asking Mr. Manager about the draft OMS manual, draft DEP, draft safety management plan, draft the storage dam commissioning plan, off-stream reservoir dewatering plan, and was asking at what stage of the design does AT expect to submit those documents to a regulator?
These are typically items that are prepared as part of the final design and submitted at that point.
And in terms of the timeline, do you have actually a timeline for that, Mr. Wood?
I don't specifically. Perhaps Mr. Svensson is aware of any timeline.
Well, Mr. Chair, this is Mark Swenson. There is no official timeline that those documents are required by, except that they are required prior to operation or the diversion of water into the structure.
Thank you, Mr. Svensson. As the low-level outlet has been sized to drain the reservoir over 30 days, what are your contingencies should a dam safety incident occur that requires a rapid dewatering of the SR1 reservoir? Maybe that would be for Mr. Manager.
Sure. So I guess to explain to the panel or the low-level outlet works for the off-stream storage reservoir is the hydraulic structure to release waters from the dam as designed. It is a concrete structure that has gates. It has a gate tower that controls flows into and out of basically out of the reservoir, and then a large conduit that discharges flows to the unnamed creek. The capacity of the low-level outlet works was determined based off of industry guidelines that were referenced and documented within the preliminary design report. Those guidelines provide recommendations for drain times in considering the potential effects of dam safety, a potential for a dam safety incident at the structure. The design for SR1 will result, or of the low-level outlet works, allows for lowering of the complete reservoir within approximately 45 days or so. The vast majority of the pool is lowered, and if I can reference the specific, one moment, I can. So Yes, so within 40 days, 90% of the pool would be eliminated from the reservoir. And that, as I said, meets the guidelines that we established, that were established through evaluation of the industry. So Mr. Secord, the proposed response is that if an issue, and this is from the reservoir being completely full. The recurrence interval associated with the reservoir being at full service level is a 1 in 200 year event or greater. It would take less time to empty it at a lower elevation. If, for instance, a 1 in 100 year has the reservoir roughly half full, and would result in a drawdown time much closer to 20 days or so. So you, in effect, but that's the case. And the reason we select that, again, is based off of a review, and the industry standards are looking at, and the reason why they have these rates are based off of an acceptable level for certain conditions and scenarios. And they take that into account. So it looks at the risk of the structure. I believe, and we selected the highest rating to use the most conservative value, as well as it looks at the consequences downstream. And so we took the combination of the two factors and selected a criteria for the reservoir to drain over that period of time.
So, Mr. Manager, I don't think you understood my question. So I'm thinking here of worst case scenarios. And my question was, as the low level outlet has been sized to drain the reservoir for over 30 days, what are your contingencies should a dam safety incident occur that requires a rapid dewatering of the SR1 reservoir? So not a leisurely drain over 30 days, but a dam safety incident that requires a rapid dewatering of the SR1 reservoir. So the question is, what are AT's contingencies should such a dam safety incident occur?
I would say, Mr. Secord, that a rapid dewatering of an embankment in and of itself could cause a dam safety issue alone. So I'm not certain of the scenario of which you're referring. It would obviously depend on the specifics of the scenario, but the most likely dam safety incidents that we would be attempting to mitigate would be those that we would mitigate with other interventions, not a quote unquote rapid release of the reservoir. You would control whether it was seepage or stability or other elements. You would be implementing other interventions.
So, yeah, go ahead.
So I'm done.
Okay, so what would be an incident that would require a rapid dewatering of the SR1 reservoir? Worst case scenarios.
I don't have a hypothetical scenario, Mr. Chairman, to offer.
Okay, you mentioned that in the event there was an issue with the reservoir, you would look at other ways of solving the situation rather than rapidly dewatering the reservoir. What circumstances were you thinking of when you gave that answer?
Sure. Common. And again, our design mitigates the majority of these scenarios, but often with embankment dams, there may be a seep identified on the downstream side of the dam that is indicating the potential for water flowing through the foundation or embankment. In those scenarios, you would mitigate by adding filters and other components to control the flows coming through the embankment and to arrest any transmission of material or particles from the embankment would be a scenario of would be one.
Are there others?
Mr. Chairman, would we be able to caucus?
Yes, please. In fact, it's why don't we do that and come back at 3:15?
All right.
Okay.
Thank you, sir.
Thank you. Yeah, thank you.
Hi, Ruth. Hi, Ruth.
Somebody's not muted, just so you're aware.
That's a good idea. Okay. That would be really, I'm actually walking right now. I'm just getting a few steps and I've been sitting down all day. But yeah, you could email me.
Okay, Mr. Weeb, I think we can get started. Thank you. Mr. Secord, so the panel had a few minutes, maybe not as much of a break as because they were working perhaps, but is the panel ready to respond or do we need a repeat on the question?
Mr. Chairman, the panel is back, but perhaps a repeat of the question would just get us back on track.
Ms. Vespa, would you be so kind as to read back the question? Thank you.
So we left off with the end of the question being, what circumstances were you thinking of when you gave that answer? Then Mr. Menninger gave a long answer about one circumstance. And then the question was, are there others? And Mr. Hebert asked to Caucus. Is that enough of a readback, or did you need the full previous answer?
No, I think that's fine. Thank you, Ms. Vespa.
So this is John Menninger. So Mr. Chairman, the most, I guess the most common issues with embankment dams was the answer that we gave. There's other scenarios potentially that have very low probabilities of occurrence, but I'm struggling to understand offer an additional example that would help inform the board at this time.
Maybe I could help you, Mr. Manager. What about a piping failure?
Sure. So, Mr. Secord, Mr. Chairman, the explanation that I provided previously. So, a piping failure for a dam is a scenario where seepage, either through the embankment or through the foundation, carries with it materials from the dam or foundation to the downstream side of the dam. In that scenario, then a void could form and cause potential issues with your structure. As I explained previously about the response to seepage, the scenario that typically is used to mitigate for that while lowering the pool is definitely a strategy for reducing the pressure upstream. Additional measures that can be implemented to help in that scenario would be to create a filter on the downstream side, and as well as add additional pressure on the downstream side, often with sandbagging and other elements. So typically you would use a graded filter and then also build up a kind of a pressure on the downstream side. It's generally the mitigation measures approved. But again, our structure has for a dam that does not have a permanent pool, has a incline filter chimney drain that goes up the embankment, as well as a blanket drain on the downstream side, that are key mitigation measures to prevent piping and control seepage through the structure. We feel confident that these measures will be effective in preventing a piping scenario. But in the case that there ever were to be, those are a common mitigation.
How long would it take to place filters in the case of seepage?
You could do it quickly. In the scenario, Mr. Chairman, under a first filling of the dam, or really in the operations of the structure, there will be a lot of eyes on the dam and the surrounding area. The plans would have multiple operators on site, as well as other staff and support, often with dams and structures, and we'll tackle this with Alberta Environment and Parks as the emergency management plans are developed, often material is actually stockpiled on site for response for certain scenarios, or there are agreements in place with contractors and other elements for quick mobilization. So this is a typical thing that's incorporated in almost all emergency management plans, emergency response plans for dams, is the identification of potential issues and mitigation measures associated with them.
You mentioned grading. What exactly is involved in placing filters in the case of seepage or piping failure?
Sure. I often realize I need to do better with communicating that term. So when I said a grade, I meant to say a graded filter. So a graded filter is a series of materials that are progressively different in size that prevent material from going from one to the next to the next. So you would go from a sand to a gravel to a riprap would be an example of a graded filter. And so basically the idea is the sand stops the clay from moving, the gravel stops the sand from moving, and then the rock stops the gravel from moving. It's basically a series of materials that help to control migration of particles.
And how would you get that material to the area where the seepage or piping failure was occurring?
Sure. So, Mr. Chairman, the dam has roads on the downstream, has a roadway on the downstream side, graded pathway for access on the downstream side of the dam, for access for equipment and other elements. So that would be the pathway.
And you would be hauling this then in the event of a flood of record, potentially days of rainfall, you would be moving this material with heavy trucks, moving it with caterpillars, cranes, that sort of equipment.
So again, this is all a hypothetical scenario, but in this situation, you would likely use dump trucks and probably front end loaders and a couple other pieces of equipment as such to transport and place the material.
Now, is SR1 a large dam?
It's long. It's it's about 3 kilometers in length. It's moderately tall. I would not describe it as a significantly tall dam. It's about at its highest is 30 meters, which is a decent size, but by other industry standards, there's much larger structures.
So it's an extreme consequence dam.
It is an extreme consequence dam.
Yeah. Is it a small dam?
These are relative terms, Mr. Chairman. I don't know. It depends on the reference point for the individual or describing it.
But in terms of its foot FSL containing 77 million or 77,000 dam cubed. Is that a small dam, a large dam, a medium dam?
I'm afraid that I can't respond to that. I mean, it holds a significant amount of water, as you said, 77 million cubic meters. I think that's appropriate for me to answer that is the design volume.
Can you tell me, did Stantec or AT use the United States Bureau of Reclamation design of small dams to size the low-level outlet?
The reference is not the U.S. Bureau of Reclamation's design of small dams. The and I guess that tells you a little bit of differential too. The USBR's description of dams, small dams, this would be a small dam in their guidelines, or at least in their reference points. They operate the Hoover Dam. That's right. So it gives you a scale differential here. We did not use small dams to design the drawdown capacity. We did use it for some of the reference points for the hydraulic analysis of the low-level outlet works.
And is there a definition for a large dam, Mr. Manager? Are you a dam builder?
I in my career, I've worked on quite a few dams in different capacities. Some that are larger and some that are smaller than SR1.
But are you familiar? Is there a definition for a large dam, or is there a large dam definition that you're aware of in your career working in the area?
I'm not aware of a criteria that would define something as a large dam. A lot of times, dam safety criteria will define a height of a dam or a reservoir pool as an element of a hazard classification. That's not the case in Alberta, but oftentimes there's different levels of classification associated with that.
So what was the accuracy of the flood forecasting during the 2013 floods for Calgary?
Mr. Chairman, I can't speak, sorry, it's Matt Wood here with AT. I can't speak specifically for the accuracy of the flood forecasting on the elbow, but what we can say is that the information was limited to some hydrometric stations and the weather forecasting. And I believe, as Mr. Menninger had mentioned earlier, some of those stations had washed out during the event.
Were they able to accurately predict water levels as required for the operation of the SR1 off-stream storage reservoir?
So, John Menninger speaking. The SR1 reservoir will utilize water level measuring at the site to be installed for the project for operations. In speaking, and Mr. Wood may add on to this, but in speaking with Mr. Frigo at the City of Calgary and those at Alberta Environment and Parks, they did have advanced warning that a large flood was expected within, I believe, from my recollection, couple days in advance. They were expecting to be ready for an event. The ultimate magnitudes and forecasts in a system like the Elbow River are more difficult to understand, but they didn't know that a flood was coming and started preparations in advance. That is the type of warning that would be necessary for operations of SR1 to mobilize staff to the site, prepare the site for operations, and be ready to move.
If I may
So-
add to Mr.
Sure,
Manager's.
Sure, go for it.
Thank you, Mr.
Wood.
Chairman. Thank you, Mr. Secord.
This is, Mr. Wood speaking.
Mr. Wood, my apologies. Yes, it's Mr. Wood. Um, one of the things that AEP has committed to is to add what they call a forecasting node at SR1. So they have a large forecasting network. It's a computer system that models and uses measured data. And in that network, they have offered to add a node there so that they have a specific forecast point for SR1. And if I may, there's one other thing, just coming back to what John said earlier about the water level. You know, technically with this structure, the structure in itself is its own gauge, and there is, although it's not a desirable way to be operating. While not desirable, the operator could simply look at a gauge on the wall of the head pond and operate the system. It's very simple in that sense. So it doesn't need sophisticated forecasting. It doesn't need sophisticated hydrometric monitoring to be able to mitigate flooding as per its purpose.
So basically the planned additions to the flood forecasting consist of this additional node that AEP is putting in, plus you said you had some sort of monitor on the head pond?
We'll have multiple redundant monitors on the head pond and downstream. Will be, yes.
And what do you mean by the head pond?
Oh, sure. That's the area upstream of our gates.
Okay.
It's basically the river for 365 days a year for 10 years, 10 years running before we operate. And then when our gates in the service spillway rise, it will create a small quote unquote head pond upstream.
And did I understand from Mr. Wood that you might have some type of automated function where once the head pond reaches a certain level, the gates then would open automatically without any human intervention? Kind of like a car that drives itself.
I actually believe that Mr. Wood's comment was the opposite, Mr. Chairman. The gates will allow for some control in specifically the service spillway. The diversion inlet gates will not open until somebody unlocks them and then goes and presses the button. Though that opens up the diversion channel. There is no reason to automate those gates. They are lack of a better term, they're binary. They're open or they're closed. The service spillway gates are the ones that control the water level in the river, as I mentioned previously. And I believe Mr. Wood's comment is that there will be what's called a staff gauge that's painted on the side of the concrete that will say what elevation the water is at. And that is the only thing we need to know how much water is going into the channel. What is the water level on the side of the structure, and that will in turn tell us how much water is going into the channel.
So the service spillway gates, those are the ones that can be operated incrementally.
Yes.
And as you mentioned, the inlet gates have basically two features, on or off, up or down.
Yeah, well, they can control flow slightly. They're not meant to be an operating gate. But no, if you close them, as you lower them, they will restrict flow into the channel.
So they can be operated incrementally as well?
Sure.
They're not totally binary then?
No, the simplest purpose for them is that during normal operations up and through the design event, they are not proposed for operating control of flows. During a dam safety event, or an event that exceeds our design event, they would lower. And so in doing that and in lowering, they would throttle the flow up until the point that they're closed.
So I'd asked you, at least it appeared to us that the low-level outlet was sized based on the U.S. Bureau of Reclamation Small Dams Manual. And you indicated that under the UBR, this would be a small dam.
So the reference for the drawdown was the Acer Technical Memorandum number 3, criteria and guidelines for evacuating storage reservoirs and sizing low-level outlet works, U.S. Bureau of Reclamation, 1990.
And that was used by Stantec? for
That is
sizing?
that is the reference incorporated within the preliminary design report and included in Exhibit 159, page 200, section 10.4.2.
And can you provide justification on why the SR1 storage reservoir should be considered a small dam?
I did not characterize it as a small dam.
So it's not a small dam.
Mr. Chairman, I think I answered this question previously. The relevance or it takes a reference point. I can tell you if the dam is bigger than another dam, given the criteria. I can tell you that the dam is up to 30 meters tall and has what the storage capacity is.
We note that the physical modeling was conducted at a scale of 1 and 16. Can you advise why a 1 in 16 scale model was developed as opposed to a 1 in 20 scale hydraulic model?
A 1 in 16 is bigger, meaning that it gives us an opportunity to better model some of the elements that we were looking to model. Mr. Chairman, for the board's benefit, a physical model is a scaled representation of a proposed design. In this case, we constructed a replica of the SR1 diversion structure and a portion of the Elbow River in a lab in Ottawa that was exactly 1/16 of the size of the proposed design. We were limited to 1 in 16 because that was the largest lab we could find. The model was half of a football field in size. It was 30 meters by 50 meters in scale. So we chose 1 to 16 because that was as big as we could fit within a laboratory in the United States. Or I'm sorry, not the United States, in North America. We looked at both. We looked both in the United States and in Canada.
Now, many flow discharge scenarios were considered for the diversion structure. Can you tell me, will these various flow discharge scenarios lead to difficulty during operations in an emergency?
If the question could be clarified, what scenarios?
Well, can you clarify what you intend to provide to operators to allow for a simple operation? Maybe that's a better question.
Sure. The general operations approach for the project is fairly straightforward. The operations of the structure will not commence until flows in the Elbow River exceed 160 cubic meters per second. That is the capacity of the outlet works, the low level outlet at Glenmore Dam. So in essence, wind flow through SR1 is 160, and roughly there's not much difference downstream to Glenmore. Then flow out of Glenmore will be 160, and Glenmore won't store anything. So that's why we chose. That's why that number is selected. Once that threshold is exceeded, we'll start to raise. Well, first we'll open those diversion inlet gates to make sure water can go into the channel, and then we'll begin to raise the water surface elevation within the service spillway. Simply, we can continue in that operating framework of a constant flow over those gates. So the water level may rise, but the flow over the gates will stay the same, or the height of flow over the gate will stay roughly the same. And that'll make sure that 160 continues downstream. And then the remainder of the flow will be pushed into the channel. So in essence, the gate operator will they know what the height of their gate is, and they know what the height of the water in the channel is. The computer will tell them what the depth of the flow over that gate is, and they'll know what the flow going downstream is. And basically they'll maintain that depth. Once the water level gets up to 1215.8, at that point, that's the maximum diversion that we want to get to. That's 600 cubic meters per second going into the channel. Once you reach that level, you're then moving the gates. If the flows are still increasing, you're now going to the mode of just lowering the gates to make sure the water doesn't exceed 1215.8. It's basically that straightforward. It's on the rising limit of the hydrograph, you're chasing a depth over our service spillway gates. So it's a simple two numbers. What's my water surface elevation in the upstream, and what's my gate elevation? And then on the receding, as the water continues to rise or flows continue to increase, once you get up to that max level, then it's simply chasing that elevation of lowering and raising my gates to maintain my diversion elevation up until the receding limb falls and we're back to the lower flow. So basically there's just a two threshold component. If you exceed all of those things, it's just gates on the ground, and water is split between the two structures.
And is there any automated function to that, or is it a case then of the operators having to react to readings that are coming into? Is there a control room of some sort?
There is a control room, and there will be computers with potential automation. We're working with the operators to understand the needs of their staff. I imagine that there will be a combination of both. The control logic for the gates will have options for automation, but I can also imagine that the operators may want to utilize manual controls in certain scenarios.
So in terms of the flood of record, the design flood, have you modeled what would be the likely scenario for an operator in the control room raising the gates? So say you had June 2013 flood coming at you. Have you modeled how these gates would be incrementally operated sort of on an hour by hour basis?
Yes.
And what would that look like from start to finish? When would the gates be down on the floor? Over what period of time would you have them basically raised to their maximum height and then drop down? What does that look like?
So during the operations, the gates will always, during that 2013 flood event, for the most part, they are operating even at 1240. They're not lowered to the ground because that's not the scenario where they would have to lower fully. They still are up. They're still raised in a slightly raised position during that, even at 1240 in the river. So perhaps some additional clarification. What type of information are you looking for in that scenario?
I'm just wondering over what period of time would the operators expect to be really needing to even control the gates in the event that a 2013 flood came at them? How much of the time would they actually be actively engaged, given that the reservoir, it looks like, is going to fill within I think it was I can't remember the reservoir fill time on the design flood, but it's
2 days.
Yeah, 2 days. I was going to say
About 2 days.
Yeah, I was going to say 50 hours.
Sure. When the gates are in operation, that it's you monitor their positions and you make adjustments accordingly throughout. This is not a,
Mr. Chairman, if I may, I believe what my colleague, Mr. Manager, is trying to say is that the AEP will be attentive to the gates throughout the operation. It doesn't matter at what point on the front end or the back end, and the amount of time is really dependent upon the flood, and specifically the amount of time that flows are over 160 in the river.
Yep.
But it seems to me this would be kind of a 2-day operation, and I'm assuming there would be maybe 4 shifts of people coming in to sort of man the operation over that 50-hour critical period.
As I said, we're still discussing with Alberta Environment and Parks, the eventual operator, on how they would choose to operate. But they would anticipate, it's my understanding, that they would utilize shifts and that they would not have the same operators on site for 2 days.
And in the event of a probable maximum flood, then the gates would be on the floor. There would be nothing for the operators to do once the reservoir was full, correct?
You're correct, they would not be operating the diversion structure, but they would certainly be assisting in any way they can, whether it would be in monitoring the structure, the SR1 structure, or assisting others.
But in terms of the gates themselves, they would be lowered, correct? Or would they still be operating the gates?
You can operate the structure to divert a portion of the probable maximum flood up until the reservoir is full, and then you would close them.
And at that point but the ones that are operated incrementally, would they be lowered in a PMF scenario?
Once the reservoir is full, and or the peak flow in the river exceeds a certain threshold.
And what happens if the gates were not lowered in the event that a certain threshold was exceeded? What are the
could you be more specific about which gates?
I'm just trying to pick up on your response, Mr. Manager.
Mr. Chairman, I believe what Mr. Secor's looking for is a scenario where SR1 is full, the diversion inlet gates have shut, and the service spillway gates are down lower to the river. And your question is, what if the service spillway gates do not lower down to the river? At that case, the gates would still be up. The head pond, as Mr. Manager described it, would still be present, and it may be rising, and that's where the auxiliary spillway would activate and allow that water to pass without circumvention of the diversion structure floodplain berm.
Yeah. And this is John Manager again. To just reiterate, the probable maximum flood, 1 in a 100,000 to 1 in a million flow scenario. And the service spillway gates have multiple provisions for lowering. in addition to, they have, you have the standard methodology. There are valves that you can bleed off the air, and they will lower underneath the weight of the water. So there's, and then there's the auxiliary spillway, as Matt said, to discharge additional flow.
At this stage, would it be fair to say that you would not have anticipated response times for operators to be dispatched in advance of a flood for the successful operation of the SR1 intake and diversion structures?
Could you please repeat that question?
Do you have anticipated response times for operators to be dispatched in advance of a flood for the successful operation of the SR1 intake and diversion structures?
Mr. Chairman, it's Matt Wood here. I can answer that.
Sure.
If I could request that the document controller please switch to exhibit 218, page 23. It shows the operational flow chart for SR1. I'll wait for you to bring it up. Can repeat that. It is exhibit 218, PDF page 23. This operational flow chart that we see here was developed by AT with AEP and the City of Calgary, who operates Glenmore. It shows how the two structures interact and how AEP plans to operate the system. What I wanted to draw the board's attention to is the area in the bottom left of that page. You don't necessarily need to zoom in, but we could, but in the bottom left of that page, it talks about 24 hours prior to a flood. And there is a box there specifically that shows that, in these certain scenarios, if a forecast suggests that SR1 may need to operate, again, I'm going back to that node that AEP will be adding to their forecasting network, then there will be 24-hour staffing of SR1. And so AEP will travel out there to address that.
Thank you. Now you can take that down if you want, document host. Can you please provide clarification on changes in anticipated water diverted if the peak of the hydrograph is missed by 1 hour as a result of response time?
It would depend on the hydrograph.
So in a design flood,
You're speaking of the two.
Sorry, Mr. Manager.
You're speaking of the 2013 flood.
Yes.
Simply a 1 hour
Yes.
change. It would not. I mean, there's built-in redundancy in our system. As I said, the diversion capacity for SR1, the required diversion rate is 480 cubic meters per second. If we were delayed an hour in raising of the gates, we could divert more, up to 600. And I guess just simple 480 divided by, that 120 extra over 4 hours. So maybe within 4 hours, you would be caught up, basically.
Mr. Chairman, if I may draw the board's attention to Mr. Menninger's earlier comment about automation, while it's not always wise to have everything fully automated, these are being considered as redundancies. Something like that could help address this. Again, that AEP may not choose to operate if no one's there watching it, but there is the ability to mitigate things like Mr. Secord is suggesting. But as my colleague Mr. Menninger mentions, in the 2013 flood, an hour would not have made a difference.
Could you provide clarification on changes in the anticipated water diverted if the peak of the hydrograph is missed by 2 hours as a result of response time?
Yes, Mr. Chairman, we have not done this analysis. We would have to look at the hydrograph and undertake this.
Can you tell me what are your contingencies during first fill that would satisfy the requirements for a first fill plan?
So the first fill plan has not been completed to date. However, I can advise the board that it will include a robust monitoring plan during the filling, including the array of geotechnical instrumentation that will be installed during construction and will be maintained during post-construction period and through operations. That would include piezometers and settlement plates and other components. The first fill plan will include provisions for the resources to be located on site for inspection and monitoring during the operations to monitor the performance of the structures, including the dam, spillways, etc. And then it will, in concert with the emergency response plans, have provisions for response to various scenarios for mitigation.
And what are summit plates?
I mumbled. Settlement plates.
And what do they do?
They are simply monuments of which you survey to observe whether or not the embankment has settled.
And the function of the piezometers?
Piezometers measure water levels within the where they're located hydraulically or hydraulically connected. So a piezometer would tell you what is the groundwater elevation in various strata. They would be placed within the embankment and within the foundations of the soils.
And would those piezometers be monitored then manually, or would they be, is there a way to, I'm familiar with piezometers in terms of contamination of sites, but is there a way for these piezometers to be monitored remotely, or is this a case of somebody having to go from one to the other and put a bale down and find out what's in there?
So there are, through, I think that part of that will be in discussions with the operator for the long-term operations of the program during construction. Our monitoring program is anticipating the use of an automated data acquisition system that would utilize data loggers that are then tied to computer systems that are then tied to communication networks. So you can easily wire up a series of instrumentation and logs through an acquisition system for display and recording all electronically.
So will these settlement plates and piezometers, will they help to address the potential risk to the structure as a result of a first fill?
Settlement plates would have less benefit. They would be part of just the monitoring of the performance of the embankment before the first fill, but they would give you some indication if there's settlement that wasn't anticipated. The basometers, on the other hand, could provide advanced or early warning of potential effects within the foundations within the foundation of the dam for elevated pore pressures or connections. So, yeah.
Are there any other elements of the first fill plan that would address and minimize the potential risk to the structure?
I mean, I think one of the key things is visual observation, and during those elements and mobiles, and having the appropriate communications strategies and plans and the appropriate contingencies in place, including the mitigation measures or intervention measures, as I said.
And Mr. Chairman, if I may, one of those mitigation measures is the ability to shut the diversion inlet gates. So as Mr. Menninger mentioned earlier, if a problem is revealed through the piezometers or the settlement plates, the operator AP will have the ability to shut the inflow to the dam to help manage the situation.
Yeah. And my colleague, Mr. Backa, I think would remind me that we also will be monitoring the flow through the drain system for the dam. So we have, as I mentioned, the chimney drain and blanket drain on the downstream side. So, and we have pipes that come out of that in daylight. So we will be able to monitor all the flows coming, if there are any, coming through the embankment, both quantity of flow and its characteristics, whether or not it has is carrying any particles or other elements.
So as the intervals between filling operations is potentially likely to be long, and operator familiarity with the structure operations during flood flow operations will not become routine, hopefully. Are you able to provide any clarification on the operator training, site surveillance, and intervals at which these will be undertaken?
I cannot provide specifics on the frequency of the training and operations, other than it will be frequent. The structure will be operated for maintenance. And I actually would invite Yvonne Carrigan from Alberta Transportation to provide a more thorough response from the government.
Yes, Mr. Chairman. I am somewhat familiar with Alberta Environment's operating procedures related to this. It's Yvonne Carrigan, sorry. So based on my experience with their other operations, and I don't expect this site to be any different, they would have annual reviews with downstream stakeholders regarding the operations if they were required, and this would be completed in advance of flood season. As well, typically at their other facilities, they're what they call exercising the gates, which means that they practice opening and closing them and reviewing all of their emergency procedures to ensure that they are prepared in the event that they need to operate.
Mr. Menninger, would you have to go from one settlement monument to another to survey them manually? And maybe you could let me know how many settlement monuments would be expected to be placed here, and how long would it take to get the data to the engineer and relay a decision to site? Sure.
So settlement is a slow process in geotechnical engineering in general. So it's not a time sensitive scenario. And if we were to do an annual survey of the monuments, it would be done in advance of flood season, and so that there would be any adverse effects that were observed. If there were to be settlement on the nature that would be of an urgent matter, it would be visually observed. I will say that.
Mr. Chairman, if I may remind, during the 2013 event, it took would have taken about 3.8 days for SR1 to fill, so plenty of time to survey those monuments if it was warranted.
Do you have a preliminary inspection checklist, including key items for review during the first fill and subsequent water diversions?
It has not been developed yet, but will be as part of the dam safety application and typical procedures for dams.
Now, I think you've provided clarification on how the operator will know at what point to divert water into the SR1 reservoir. And basically, as I understand it, anything over 160 cubic meters per second, you start to divert, correct?
That is the threshold for diversion. That does not mean that the operator has to divert. If based off of their information, it's going to go to 170, then drop back down in the next couple hours, it may not be worth, the water might not make it to the reservoir. It may just dry up in the channel. So there are conditions different that may differ, but typically for larger events, that is that threshold and would be the proposed operating scheme.
And again, Matt Wood here, if I may, for the benefit of the board, the exhibit I referred to earlier, you don't need to bring it up, but that also shows those considerations for operation.
And I think you have indicated certain conditions when diversion would cease. But are there other circumstances that we haven't discussed or other conditions that we haven't discussed where diversion would cease?
The conditions primarily are, number one, if the reservoir is at capacity, diversion will cease. If the water level if the flows drop below 160, diversions will cease. And then the other one is that as the mitigation measure mentioned earlier, that if there are observed issues with the dam or the channel that would require intervention, then the gates will be lowered and diversions would cease. Those are the three scenarios.
And I think you've addressed this to some degree in terms of what are the anticipated windows of time in order to respond to an emergency, and what are the mobilization times for various personnel, equipment, and materials. Obviously, you would expect to have personnel on site fairly soon in the event of a flood event occurring. So that would deal with the personnel. But what about equipment? What would be the anticipated windows of time to get equipment on site? Or would equipment be on site 24/7?
I think some of those plans are still in development, but I think in coordination with Alberta Environment and Parks, those will be established and be part of our flood action plan and incorporated within our submission.
So my understanding is the intent is not to provide stop logs for the intake diversion, and the window of opportunity for low water is estimated at 2 months. Can you please provide clarification on how major maintenance such as gate rebuilds which typically take longer than 2 months to complete, will be undertaken in the future?
I'm uncertain of the 2-month reference that you're providing. Could you clarify?
My understanding is it'll take 2 months for the water to be removed from the reservoir, correct? 60 days? Or is it 30 days, I guess?
Okay. So the gates are above, and you're speaking of the diversion inlet gates?
Yes.
They're above the reservoir elevation, and they're above the normal water levels of the Elbow River. They sit in the dry.
So if they needed to be overhauled, then there would be no issue given their elevation?
Correct. If it was long enough and they needed to be to a greater degree, a temporary cofferdam could be constructed. But I don't see that as being a typical, that would be a very rare occasion.
If I may, Mr. Chairman, it'd be, I think, safe to assume that AEP would not be looking to overhaul gates immediately after a flood. This would be something that would be planned well in advance as part of the maintenance program, and would be planned outside of the restricted activity period in the river and at periods of low flow to mitigate the risk of overtopping of any cofferdams.
Can AT clarify your intentions for public safety and security at the facility, including warning systems and intended means and methods to keep the public from accessing the dry reservoir and or alerting the public that the reservoir is about to be filled?
Mr. Chairman, would we be able to caucus on this? We could be quick.
Yes, please. Yeah, proceed.
Thank you. Thank you, Mr. Chairman. We're back now.
Okay, thank you.
All right. So, Mr. Chairman, I should start with that safety of the public has been a key consideration of many of the items that we've incorporated within the design of SR1. And I'll start with, many of our spillway structures, you'll notice, do not maintain permanent water pools in them. Typical for hydraulic structures at dams would be to have stilling basins that have a low point that would have water in it full time. as this is a large site that's difficult to control access, we've incorporated design measures to eliminate pools like that that could be a potential drowning hazard to the public, as an instance. Many of our structures, or all of our structures that have fall potential, have railings and other fall protection measures that if the public were to, to be on, that they would then, there are railings and other components to assist. The service spillway gates, among some initial concepts and in many diversion type structures, they are a elevated weir that could provide potential for hydraulic rollers and other things downstream. These sit at the flush bed of the river and allow for that component. So just to start with, safety has been that piece of it has been a concern, and has been definitely at the forefront of the design team through the process. So with regards to the public, we're handling safety in a couple of ways. Number one, restricting access to areas of security for the property and that could potentially be more adverse to the public if they were to access. The area in and around the diversion structure, including the control building, will be fenced with chain link fence and security materials in that area. The remainder of the site, so that's a fairly limited location, I should say. It's that parking lot, I think, that we looked at before on the drawings. Generally, that area will be fenced to prevent that's really the only location where we have like high walls and things like that could be a potential of serious concern for fall. The other areas of the site will be designated as by the project, with fencing, for property fencing, and with notification that they're entering a project and location. And then there will be significant signage throughout to inform the public, both along the Elbow River and throughout the reservoir, of their presence within the SR1 site and its function as a flood control reservoir. So there's so basically, number one, there's the design. Two, there is the hard access requirements from that the high security areas. Three, there's the more passive property designation and notification. And then the final piece here is the signage, or four is signage and communication. And then five would be the additional layer of requirements prior to any operation, including inspection of the facilities in advance, and clearing of the potential public. We do anticipate that the emergency management plan or the flood action plan will also incorporate notification of nearby, potentially nearby affected areas as well. So,
Mr. Manager, you mentioned security materials at the parking lot. What were you referring to there?
Primarily, it's just it's the chain link fence and locks.
Okay, so it's not proposed then that people will be flocking to the parking lot to see the gates rise on the Elbow River.
They will not be permitted.
And you're not going to have school kids standing on the access bridge, gawking at the water as it flows through into the reservoir.
They are not permitted. Although they could stand at the top of the slope and have a nice, safe, distant view of it.
What do you mean by the top of the slope?
The channel has a large, long slope downstream of the diversion structure. The channel is about 35 meters deep, and it's a big, large vista from up top there. So That's an area that would be outside limits of the project, that if somebody wanted to observe the project from a safe distance and be outside of the project area, that's a potential location where they could observe. They would probably be on private land at that point though, so they would have to obviously clear that with whomever they were accessing.
And in terms of the reservoir itself, will there be attempts to keep school kids and others off the top of the reservoir structure as it's being filled?
We would certainly propose that during operations that the area is a controlled location and that it should only be accessed by the staff that are in operations or those that are assisting them in operations and of the dam. This is but that again, this structure will be operated likely on the order of a once every 10 years event, and for a couple months, a month-long window at a time. During other time periods and times, access to the public could be.
And the parking lot itself, will it be permanently chain link fenced and locked off where the control building is?
At the control building, yes.
Yeah.
Yes.
All right. What is a fracking exclusion zone?
A fracking exclusion zone, as I understand it, is a area around a particular location for which fracking is not allowed, is my understanding.
As the response to the proposed fracking exclusion zone only addresses the ground accelerations at the dam site and does not appear to address issues surrounding settlement, should fracking occur close to the dam or allow for a settlement beneath the structure, can you tell me how do you intend to mitigate this risk? And this might be a question for Mr. Back, perhaps, I don't know. But by all means, Mr. Manager, if you want it to field it.
Could you repeat that again first?
Sure. So as the response to the proposed fracking exclusion zone only addresses the ground accelerations at the dam site and does not appear to address issues surrounding settlement should fracking occur close to the dam or allow for a settlement beneath the structure, how do you intend to mitigate this risk?
This is Dan Back. I believe the greatest risk to the facility would be the motion from fracking. I don't think in the formations here that we would have a significant risk of a fracking operation causing significant settlement. Now, if there's resource extraction, if there's oil or something being removed, there may be a different situation, but the danger typically associated with fracking is the motion that comes from fracking-induced seismicity. That was evaluated in our seismic hazard analysis. That's what you alluded to in your earlier comment. As far as settlement, I'm not aware that there would be any issue if it was an area settlement, then everything would settle together, the dam, the reservoir, the channel. As far as differential settlement, the monumentation that's supposed to be on the dam would allow us in regular intervals to make measurements of that and establish if there's a differential settlement occurring at the site. And mitigation could be undertaken prior to the use of the facility.
And Mr. Back, what is a fracking exclusion zone?
That term was brought up. I would have to assume, like Mr. Manager, that would mean an area where fracking would not be permitted. As far as I know at this point in time, aside from the government-controlled property, there has not been a fracking ban instituted at the SR1 site.
I'm sorry, I missed that, Mr. Back.
As far as I know at this time, aside from the government-controlled property, there has not been a fracking ban instituted at the site. I could go on to say that as far as we know at this time, there hasn't been any fracking that has occurred in the vicinity of the SR1. There is fracking in Alberta. It's a number of kilometers to the north and northwest where that has occurred.
So where is the nearest, do you know where the nearest resource extraction is to the project area?
Do not. I know that there was some gas extraction not too far away. I think oil extraction is probably a little farther north, but I couldn't give you specifics.
And Mr. Manager, this is probably a question for you or for Mr. Wood. Could you please provide clarification and justification for the constant diversion inlet rate of 480 cubic meters per second during routing of the probable maximum flood, as this appears to be inconsistent with inlet gates being fully open and assumes that the gates can be partially closed, which impacts the sizing of the emergency spillway? So maybe I might just, maybe I should rephrase this question, more as perhaps as a proposition, and you may dispute various elements of it. So I'll just run it by you again. And can you provide clarification and justification for the constant diversion inlet rate of 480 cubic meters per second during the routing of the PMF, as this appears to be inconsistent with inlet gates being fully open and assumes that the gates can be partially closed, which impacts the sizing of the emergency spillway?
Sure. So in fact, what we're showing is that the gates can't be closed. We're actually increasing. So the hydrograph that's shown on, I guess we can reference it for the board on exhibit 159 on page 177 of the PDF, is a scenario where, as I mentioned, the probable maximum flood and we have a malfunction. And so in this scenario, what we're demonstrating is an initial diversion of flow into the reservoir up until a point where we lose control of the inflow. So it does look a little bit strange that the hydrograph rises and then flattens at 480 for I guess those blocks 4 hours or so, and then spikes back up as inflow continues into the reservoir. What that's actually showing is that the service spillway gates are in control of the flow into the channel up until the point that the water continues to rise faster. It's not showing that the gates are closed and throttling flow or partially closed and throttling flow. It's that we're actually operating the service spillway gates to push more flow in. It's almost like we're pushing. Oh no, we can't stop it scenario, not we're throttling it and then the opposite scenario. So this is in fact a operations scenario. In a very large flood, and if you wanted to capture the peak of a very large flood, you would not want to fill your reservoir before the peak got there. So we are using a lower volume because we thought that that was a realistic scenario for operations during that period of time. And after that point, and I will continue to say that this is an incredibly conservative scenario. This involves the probable maximum flood entering our reservoir without any intervention to prevent flow. We are not assuming the gates are closed one bit. Not that they stopped halfway closed, that they never even lowered, and that the full uncontrolled piece goes through. So just to clarify, I mean, this is a scenario where we have an extra spillway and designed to pass the 10 to the minus 6 event, and we're assuming that there is zero intervention for a period of 3 days. So I will, but that's the seriousness that we're taking the extreme hazard structure of this facility.
Now, on Monday, you you mentioned about the operator being able to vary the inlet rate between 480 and 600 cubic meters per second. And we've discussed, that I think to some degree. And you mentioned basically there's the ability then to essentially capture the peak of the hydrograph. Did I hear you correctly?
I said that is a strategy that could be employed during operations.
And how do you know when the peak of the hydrograph is going to come?
Yeah, you don't, Mr. Secord, and Mr. Chairman, you don't know for sure when the peak of the hydrograph is going to come. You will have some information coming from upstream. We will have an understanding of rainfall in the areas and things of that nature. So there is, there's potential, there is not, but in a scenario where we do have gauges upstream, likely multiple flow gauges telling us what's coming, there is some scenarios where you could foresee it, but I can't say that you will always know what the peak is. But that also supplies you with the simplicity of the operations. We have a target to operate between 480 and 600 cubic meters per second, and that is sufficient to mitigate billions of damage in Calgary for a flood of up to the 2013 flood. So that's.
Could you please indicate the means and methods for cleaning up the debris deflector and contingencies for debris accumulation during a significant flood event should this occur? And I don't know, Mr. Manager, whether you were there during Barbara Teitmeyer's presentation, but she showed a picture of the inside of her house with this huge log in there, which she said once it got in there and the water came in there, she said it was like a washing machine inside her residence. So I'm just wondering, it looks like the stuff that could be coming at this debris deflector could be, significant in size and potential to damage. So if you could maybe speak to that question.
Sure. I think the to your point, and for the benefit of the board, debris is a significant concern that the design team has had in place and in mind from the outset of this project. Starting with the diversion structure, the changes that we made from the concept design that had overhead radial gates in place within the structure, and replacing them with crest gates that allow for debris to flow over top of them was one of the initial first decision points that we made as part of the project team in order to mitigate for debris. So the debris deflect, so those were tested, and part of the reason how that was arrived at was that we did test debris within the physical model. So we actually crafted scaled trees and put them within the model to demonstrate their effect. The trees also had roots. We put real root balls on the ends of the trees to simulate that effect. So the intent there was to make sure, how do these gates operate with debris, and can we pass debris over top of them? So one of our mitigation strategies is to promote for debris to continue downstream, to stay in the Elbow River and pass through our structure. Recognizing that during some of these bigger flow events, when we're going to have potentially more flow going to the diversion than going downstream, we weren't going to be able to keep debris out of the reservoir and away from our diversion inlet. So we proposed this debris deflection barrier that's now incorporated within the design. That was also tested within the physical model. But in terms of the design elements of it, that debris deflector has been designed to consider impact loads from very large debris and beyond. So the impact is one thing. So we looked at, and Matt had a key role in this. We did look at impact loads from trees and from large trees, right? But we also looked at an impact load from a Ford F-250 coming down the river and hitting it. So we looked at the velocities going into it and their contact with those structural members. Probably more the more structural one that we looked at though was we considered the effect of like drag force pulling a large mat of debris up against that deflector. And designed it accordingly. It is long. I think it's been mentioned here that it's 170 meters in length. So, and by contrast, the diversion inlet gates are only 40 meters total. So if you can consider that in terms of blockage, that structure has a ton of flow area. So getting flow, what we've shown through our hydraulic calculations is that getting flow through that structure will not be an issue during these design events. And then finally, to your point, again, we designed it to promote, where possible, debris to stay in the river and continue downstream. But in this scenario, that if wind debris, it gets within the structure, either up against it or within the channel, there's provisions for cleanup. And maybe I can have Matt Wood describe how we would propose to perform some of those activities.
Just before we get to cleanup, and Mr. Wood, definitely I want to hear from you on this. You said you modeled a Ford F-150 coming down the river. Did you model a house down the Elbow River?
Yes. So thank you, Mr. Chairman and Mr. Secord. That is a good question. It's one that we have actually received as well. I will correct Mr. Manager. It was an F-350, a one-ton diesel, given that this is Alberta. But, when you have the house itself, and I know there's a very famous video from one of the residents in Bragg Creek who lost their house, unfortunately, to the flood, where the house comes down and slams into the bridge at Bragg Creek. You see it break up, right? And so the impact from that is maybe not the same as a hard, dense, heavy object, and that's where the truck came in. But to that point, when things like say a house, or we even talked about tarpaulins could have the same effect, right? Like anything that's a blockage of the structure, a piece of sheathing from a house, a picnic table, all those things that have blockage faces could accumulate on that. And to Mr. Menninger's point, the structure has been designed with a lot of area. If you think of the lint screen in your dryer, right? This is like, it gets accumulation on it, so you make that screen bigger so that the air, in this case, the water, can still move through it.
And again, before we get to you, Mr. Wood, on the cleanup portion, do I understand it, Mr. Menninger, then that in this sort of football field or half football field model that you created, you actually did you actually create the deflector barrier and then trees with roots balls on them, and then essentially created a channel which would then have had a flow velocity of, let's say, 1,600 cubic meters per second, and then actually are you actually testing, building a model to actually see what happens on a small scale? Did I understand that correctly?
Yeah. Yes, we tested it up to the design flood event with debris, and it was basically a three-dimensional model of the Elbow River. We even embedded sticks into it to represent the forest upstream of the floodplain berm. All those features are incorporated in it.
And to be clear, that's we're not talking about a computer model. We're talking actually a physical model where you get water, you generate a certain flow velocity, and then you observe what occurs in the model itself. Do I have that right?
That's correct. And the details of that are in Exhibit 174.
Right. All right. And so I had asked then about the means and methods for cleaning up debris accumulation during a significant flood event, should this occur. So in a scenario where you have somebody's, a tarpaulin from, covering, a 100 or 200 round bales, or, something like that, hitting the debris deflector, what are then the contingencies for getting that removed from the deflector?
So, Mr. Chairman, if I may, just maybe a correction. I'm not too sure if you intended this, Mr. Secord, but the cleanup wouldn't be necessarily during flood operations. It would be in post-flood operations when it is safe to get in there to remove it. As Mr. Menninger explained and designed, the debris deflection barrier is intended to accumulate sediment, and it's been designed to or accumulate debris, and it's able to do that. So you wouldn't go in and actively remove it during a flood, but after a flood, once those service spillway gates, I'll be very quick. Once the service spillway gates drop, that head pond that Mr. Menninger mentioned would lower, and debris removal from the barrier can be done in the dry.
And so I guess I think you've answered this, Mr. Wood, or I guess the answer, I assume, is the impact to the intake diversion capacity during such debris blockages. Would I be fair in sort of inferring then that you don't expect there to be an impact on the intake diversion capacity? Maybe that's more for you, Mr. Menninger, but either of you.
Sure. So this is John Menninger. There will be some effect, right? You can't there, but it will not affect our ability to divert and meet the thresholds for the 2013 flood based off our simulations. And we looked at a significant degree of blockage, but like I said, it is 4 times the width of the diversion inlet.
Can you please indicate the conditions under which Springbank Road will require a closure during the operation of SR1 reservoir?
So it would be at the point where the water is within a certain distance of the pavement. That elevation, I believe, is about, based off of our transportation engineers' recommendations, is within a meter. I think there are other safety considerations that probably need to be in place for confirmation on that. And during diversion, I would expect that we'd have to consider those elements. So I think some of that's part of the flood action plan that will have to be put in place. But
and if I may contribute to that, Mr. Chairman, Springbank Road doesn't overtop until a 50-year event. That's been indicated throughout the length of the project. I believe what Mr. Menninger is referring to is that even though it may overtop at a 50-year event, there would be monitoring of it. And what he's referring to is the substrate underneath. You may not be able to drive heavy loads on it and stuff once you're at that point just below the pavement. So it may be just before the reservoir is full with a 50-year event.
Okay. And who will be responsible for the closure of Springbank Road under these conditions?
I believe that's still that'll be determined as part of the operations plan in conjunction with Alberta Environment and Parks and Rocky View County.
Okay. And so in terms of providing resources for the closure of these roads under these conditions, again, that would be something to be determined in the future.
That's correct.
Okay. Mr. Chair, I'd like to, if I could, turn to exhibit 339, but if it's okay with you, could we take like just a 5-minute stretch break for a minute or two?
Sure. Well, we could, and I mean, I'd like to wrap up probably around 5 o'clock today if we could, but we can go, I mean, a few minutes past is fine. So if we want to just take 5 minutes for
just a couple, maybe just
2 minutes.
come back in about 3 minutes.
3 minutes is fine. Yep.
Great, thank you.
3 minutes, and we'll be back and we'll close shortly after 5.
Okay.
Mr. Secord, are you ready?
Already, thank you, sir.
Okay. No, that's good. I mean, what with
I apologize. My 2 dogs came into my office and informing me that they were ready for their dinner. So I had to shoo them out. I'm sorry.
Okay. No, the life of a virtual world. Okay.
That's right.
Yeah.
If we could
Please-
go to
please
PDF,
proceed.
sorry, if we could go to PDF page 7. And Mr. Manager, are you familiar with the Alberta Dam and Canal Safety Directive?
Yes, I am.
And you can confirm this document has an effective date of December 11, 2018 and would apply to SR1?
That's correct.
Okay. And if we could turn to, where are we here? section 2 part 2, section 2.1, at the bottom of that page, it says information required for a new dam or canal. One, when applying for an authorization to construct a new dam or canal, a dam canal owner must submit to the director in writing all of the following information. And can you advise whether all of the information set out in section 2.1 has been filed with the NRCB?
Sure, I'd be happy to explain that. So the answer is not everything has been filed with the NRCB or with the Dam Safety Review Board or reviewers at this time. In our discussions with the Director of Dam Safety at Alberta is that this process is, while not laid out explicitly in the directive, is a, what's a term I'm looking for? It is a kind of a stepped or phased process for submission of an application. And I'll give you a reason why. If I could reference you to section C or V or section C6 on page 9, it also requires a construction completion report. We can't complete construction without authorization, and so you can't submit the full requirements. That's just one example. So there's multiple expectations here from the reviewers that you first submit your hazard classification and your preliminary design information. That information is then provided to the agency, to the department, and they review it. And they provide comments and feedback about those elements. Those components, and they will advise if they need additional information, are basically the elements in order to get approval for construction, if you will. And then the next stage gate that you're at is that during construction, you would then develop that operation, maintenance, and surveillance manual, your emergency management plans, response plans, all these other elements that we're talking about. And there's a reason why. So your operations manual for a dam incorporates all the elements associated you have to do to operate those mechanical and instrumentation components. Well, when you do gate procurement and design for a project like this, you don't specify one manufacturer or one supplier. You put it out for bid with requirements for performance specifications. And then the contractor goes and procures something that meets those requirements, and then it's reviewed and approved by the government. So we can't write an operations manual until we know what specific equipment needs to be operated. So that's just one example, but then the construction completion report is another. So basically it's a staged process to get through the dam safety review process with them. And so we are in that process. They have been provided the hazard classifications and the majority of information that's in those first sections of this element, including site characterization and analysis and things like that nature.
So in terms of the regulatory process, AT applies to the NRCB for authorization then to build SR1, correct? You're looking for an approval.
I guess maybe someone else in the panel would be better to answer questions about authorizations of the NRCB.
Mr. Hebert?
Mr. Chairman, Mr. Speller will provide the response on this matter.
So, Mr. Chairman, we're applying through this process to the NRCB for permission to proceed with the project. The authorization to build the project and the acceptance from the dam safety reviewers on the design of the project come through Alberta Environment and Parks and their approvals teams.
So you get, Mr. Speller, are you hoping to get an approval from the NRCB, and then at some point in the future, then you would also be getting an authorization to construct as well from the director?
From the director of, a director at AEP, yes.
Okay. And then if we look at page 9, for instance, that Mr. Manager referred to, he refers to just above that, it says that you're to submit to the director Roman 5, capital E, testing and commissioning. What is involved in testing and commissioning that the director wants to see?
Sure. So that as part of the design, we're developing requirements for the performance of a number of mechanical and, like I said, electrical and other instrumentation components, structural components that will have to be proved out in, prior to acceptance by the government and handover. So in this scenario, if you're talking about a gate system, the commissioning of that gate system would consist of the operation of those gates through the full cycle as an expectation as part of the commissioning process.
Now, Mr. Manager, my clients would like the opportunity to review this information as part of the approval process. It looks to me like obviously we're not going to have testing and commissioning happening before the NRCB decision, but would AT accept as a condition of an NRCB approval a requirement that the testing and commissioning details would be shared with the SCLG? That might be a question for Mr. Hebert, perhaps.
Mr. Chairman, if we could caucus quickly on this, if you don't mind.
Right, just looking for my mute button. Yes, please. And
thank you.
Mr. Secord, it's on 5 o'clock. So, is there a logical question or two, and then for a break, and then we can continue on tomorrow morning?
Maybe what we'll do is we'll hear from them when we come back, and we can break now and resume at 8:30 tomorrow morning, sir.
Yes.
Okay, thank you.
Yes.